You know that glow? You've seen it, right? That iconic electric buzz that lights up a city street or spells out open in a window? It feels so familiar, so neon. But behind that light, there's this incredible story that goes from a dusty lab in London all the way to the very heart of our digital world. So let's dive in and see what's really going on behind that glow.
I mean, we see these signs all the time, but have you ever really stopped to think about it? Like, what's actually happening inside that bent glass tube to create such a bright, vivid light? How does a simple, totally invisible gas become this beacon of color?
Well, it's not magic, but it's something almost as cool. It's physics. It's this beautiful, surprisingly simple dance where you take a jolt of electricity and a very special element and you smash them together to put on a light show at the atomic level.
Okay, so let's start with the classic, that image we all have in our heads. The glowing red sign that's been the star of everything from old-school diners to entire city skylines for what, over 100 years now?
The actual setup is ridiculously simple. Seriously, you just take a glass tube, you suck pretty much all the air out, and then you pump in just a tiny bit of pure neon gas. Then you stick a metal electrode at each end. That's it. The real secret isn't the tube itself, it's the gas that's trapped inside.
So you flip the switch. What is going on at the atomic level to make it light up? This is where neon, as an element, really gets to show off its unique properties. It's kind of perfect for the job.
See, neon is what we call a noble gas, and you can see its electron setup right there. That outer shell is completely full. And what that means in simple terms is that neon is super stable. It's very unreactive. Honestly, it's kind of aloof, you know? It doesn't like to bond with other elements. But that stability, that's exactly what we need for this to work.
Okay, think of this like a game of atomic tag. First, you hit it with a high voltage, forcing electricity to rip through the gas. This energy knocks electrons loose from some of the neon atoms, creating this charged-up soup we call a plasma. Now, these freed-up electrons start zipping around and bam, they crash into other stable neon atoms. This collision gives those atoms a jolt of extra energy, putting them in an excited state. But here's the thing, atoms hate being excited. All they want is to be chill and stable. So almost instantly, they dump that extra energy to get back to normal.
And this is the magic moment. That burst of energy they release comes out in the form of a tiny particle of light, a photon. And for the element neon, that photon has a very, very specific amount of energy, which corresponds to a wavelength our eyes happen to see as that iconic, unmistakable reddish-orange glow.
Right, this is probably what you're thinking. We call everything a neon sign, right? But if pure neon only makes that one red-orange color, where are all the blues and the greens and the pinks coming from?
Well, the first trick of the trade is pretty straightforward. You just use a different gas. As you can see here, if you fill that tube with argon instead, you get this really nice soft lavender blue. Helium gives you a kind of pinkish gold, krypton gives off a pale white, and xenon a really rich blue.
But the real secret, the way they get that huge rainbow of colors, is this. They coat the inside of the glass tube with different powders called phosphors. See, gases like argon actually produce a lot of invisible ultraviolet light. When that UV light hits the phosphor coating, the powder itself freaks out and emits its own visible light. And by mixing and matching these different phosphor powders, artists can create over 150 different colors. Pretty clever, right?
Okay, so that's the science. But the story isn't just about atoms and electrons, it's also about a huge moment of human discovery. I mean, neon wasn't just lying around waiting for us, it had to be found.
So picture this, it's 1898. Two chemists in London, Sir William Ramsay and Morris Travers, were messing around with liquid air. They managed to isolate this new gas they've never seen before, and when they zap it in a spectrometer, it just lights up. 12 years later, this French engineer, Georges Claude, figures out how to trap that glow in a sealed tube. And by 1923, the whole idea jumps across the Atlantic, where the first signs are sold to a Packard car dealership in LA. And get this, they nicknamed them Liquid Fire.
You can just feel the pure awe in this quote from Morris Travers, one of the guys who discovered it. Can you imagine being the very first person on the planet to see that color? He said, "The blaze of crimson light from the tube told its own story and was a sight to dwell upon and never forget." Wow, what a moment that must have been.
But the story doesn't stop with cool signs and advertisements. As awesome as neon signs are, the element itself has some other, much less famous jobs that are actually incredibly important.
So you've got neon and its familiar gas form, which is used in things like high-voltage indicators and, really importantly, in lasers. But if you chill it down to an insanely cold -246 degrees Celsius, it turns into a liquid, and that opens up a whole new world of uses.
And check this out. As a cryogenic refrigerant, liquid neon is an absolute powerhouse. For the same amount of space, it has over 40 times the cooling power of liquid helium. That makes it wildly efficient for anything that needs to get extremely cold and stay that way.
And this brings us to the final, and frankly, the most surprising chapter in the story of neon. It's one that ties this simple glowing gas directly to global politics and the very foundation of our modern economy.
Just take a look at this chart. The single biggest use for neon today? It's not lights, it's not refrigeration. Almost half, 45% of all neon is gobbled up by the semiconductor industry, the people who make computer chips. So, why do they need so much of it?
The answer is a process with a really complicated name: deep ultraviolet lithography. Basically, neon is a critical ingredient in the super high-powered lasers that are used to etch microscopic circuits onto silicon wafers. It's how we make the microchips that power, well, everything: your phone, your car, the whole shebang.
Now this is where the story takes a sharp turn. About 70%, 70, of the entire planet's supply of high-purity neon comes from just one country, Ukraine. And it's not even mined there. It's captured as a byproduct from old-school steel factories.
And when your supply chain is that concentrated, things can get volatile fast. After Russia annexed Crimea back in 2014, the price of neon shot up by 600%. It sent this massive shockwave through the entire semiconductor industry.
And things got even more serious in 2022. The full-scale invasion shut down the two main Ukrainian companies, Cryowen and Inhaz, that, together, were making about half of the world's entire supply of semiconductor-grade neon. The entire global chip market was suddenly at risk.
So think about that. An element that was discovered by accident, an element that defined the look and feel of our cities for a century, has now become a massive choke point for the most advanced technology we have. The glow that lit up Main Street now highlights just how fragile our global supply chains really are. And it really makes you wonder, doesn't it? What other simple materials are out there, holding our entire complex world together by a thread?